All right, everybody, let's get started. I think that the word of the day is burr. It's cold. Cold enough that I thought it appropriate to throw a little meme on the announcement slide. So that's Sub-Zero from Mortal Kombat and Elsa from Frozen, in case you didn't get both references. It's cold today. I was saying before class, I feel particularly for my CAD class, because we were running out of space, and so I had to move the class from Corbly to the business building. So we have a walk today throughout all of this, so I'm sure they love me right now. So, okay, how did homework 1.2 go? I know there was a couple of lookup challenges, but hopefully, like, at least conceptually, it wasn't very difficult. Today, we're going to begin what I would call our first real foray into steel design. And what we're going to do is we're going to focus on tension members, okay? We focus on tension members at the beginning of this class for a very specific reason, and that is the following. Of the elements that we analyze and design as structural engineers, tension members are among the easiest, at least to sort of conceptually understand. But we're worried about more than just learning how to analyze and design tension members. My first real goal is for you all to understand how to navigate this, okay? And so if we're going to learn how to navigate the manual, it would be best to do it with a topic that is relatively straightforward. Like, let's not start with beams. And there, I have actually debated starting with beams, in this class, but I think with starting with beams and orienting you to the manual, it's sort of a lot. I'd rather just take it easy. I would mention that I would say the two most common examples of tension members in real-world structures are braces. So if we're talking about a lateral brace that's meant to withstand wind and seismic, that's one example. Another example is a truss, right? The tension members, remember when you solve a truss, the members can experience either compression or tension, so the tension elements inside a truss. And we're going to look at both of those types of examples throughout this semester. So, but we got to walk before we can run, so we're going to take it one step at a time and just sort of get a handle on what we're talking about here. Did everybody get the code? Did you get the code? Everybody, look, he's getting the code. He got the code? Okay, all right. I can't help it. Sorry, I can't help it. Okay. All right. Let's talk about tension members, okay? And we're going to begin our discussion with just recalling the idea of a limit state, okay? And remember, a limit state is a condition that we as the structural engineering community define, and we say that once you have violated this condition, the member is no longer fulfilling its intended function. And we split this up into two main classes of limit states. We have strength limit states and service limit states, and for tension members we are going to assess both. The strength limit states are going to be related to the load that an element can withstand before it fails. Serviceability for tension members is going to relate to something called slenderness. I will get to what that means a little bit later, but for now, just say that we are going to place a limit on the slenderness ratio for the purposes of construction and erection of a given steel frame. If a member gets too slender, it gets a little bit hard to handle on the construction site, and while there's not a hard-coded requirement in the manual, and we'll talk about what that means a little bit later, we are going to employ it in here, and most structural engineers in practice do. Okay, so let's go back to basic mechanics, okay? And so what I'm basically saying here is, okay, I have a member that is subjected to axial tension. So I'm taking this element and I'm yanking on it, okay? Now, I'm going to go back to Basic Engineering 216, to Basic Mechanics of Materials, and I'm going to say that let's recall that formula. Okay, does everybody remember that? Sigma equals P over A. So it's basically just Pressure for solid mechanics, right? We don't deal in pressures. That's a fluids land term. We deal in stresses in solid mechanics, right? So the idea is if I have a load applied to a section and I know its cross-sectional area, I can determine the stress as sigma equals P over A. Everybody with me on that? So what we're going to do is sort of look at it a little bit from a flip-sided perspective. What we're going to have is we're going to have a tension member, and we're going to say, okay, we know what that area is, or later on we're going to have to solve for that area, and that's going to be our design side of things. But our stress is going to come from the limiting stress for a given material, things like Fy or Fu. And so if I know the stress and I know the area, I can determine the load. And all I'm doing is I'm just multiplying both sides by area. And I'm saying that the area times some limiting stress equals P. And that's what I'm getting right here, is I'm basically just saying that the load equals some limiting stress times an area. Does that make sense? Okay. So I want to take a look at a tension member. So let's just sort of take stock of what I'm looking at here on the screen. So I've got here a piece of steel, and I'm yanking on it in tension. So the loads are intending to stretch the member, to make it longer. And notice how I've identified connection regions on either side of the member. And this is where it's starting to get a little real world. Like, you probably didn't talk about this in Engineering 216, but in reality, it's not just a prismatic member. You're going to have a connection region on either end. And now we've got to look at that stuff. Okay? With me so far? Okay, so what we're going to do is we're going to focus on two sections. And when I mean sections, I mean, remember, I've got the samurai sword or lightsaber if I'm a sci-fi fan, and I'm going to cut a section through a member, and I'm going to investigate the stresses or what's going on around that section cut, okay? I'm going to do the same thing here, but I'm going to pick very specific sections, okay? And I'm going to term those the gross sections and the net sections, okay? Now, the gross section is just anywhere in the main body of the member, okay? Just somewhere in the main body. And the gross section is sort of defined as anything away from the connection, just anywhere in here, okay? And the idea is it really wouldn't matter if I cut a section here or here or here, because it's all the same area. With me so far? Okay. Now that's the gross section. Here's the net section, okay? Now the net section, I'm going to say, is through the region where the connectors are, okay? Now let's go through a couple things. First off, this little schematic I drew here on the slide is showing the net section on the right. Is there anything different on the left? It's the same thing, right? So, you know, you're really only going to evaluate one side of the tension member. You don't need to look at the other, unless the connection scheme was different. But I do want to keep in mind that we are sort of discussing real-world applications in here, and I can't think of many real-world applications where you would have a significantly different connection region over here than you would over here. Maybe some bracing configurations it's going to be a little different. That's entirely possible, bless you. But more often than not, we're going to try and keep things simple. Okay? The other thing, so again, whether I was looking at the left side or the right side, it wouldn't matter. Now, the important thing to note, and I'm going to ask that you trust me right now, and I'll explain a little bit more later about what this means later. But the important thing is that the section that we cut passes through the lead line of bolts, okay? And for our first foray into gross and net sections, it's not really going to matter because the math would be the same. But suffice it to say that the lead line of bolts, if here's the tension member, the lead line of bolts is the section cut that's like closest to the middle of the member. So instead of cutting here, 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 we're cutting here because it's closest to the main body of the member. So this would be the lead line of bolts, and this would be the lead line of bolts. So we're talking about this and that, okay? Later on, when we start having staggered bolt arrangements, we're going to have to identify the lead line, and there'll be some discussion there. But for now, it's you know, you'll see here in a bit, it's not really going to matter for our first foray into it. So far, so good? Okay, all right. So let's open up the manual, okay? So just so everybody's aware, if you've got your manual with you, okay, I am in this back part here of the manual, so this is section 16, and you'll notice the page numbers will say like 16.1, 16.1-11, 16.1- what have you, and I'm on 16.1-32. which hopefully should be a little bit familiar since I referenced this in your last homework assignment, okay? Now, I will say this, we're not going to use this section of the manual, like, we're going to review it, but this isn't something that you probably need to tab or something. It's probably more something that you need to just make sure you have on a formula sheet if we have in an exam. There is a section in Chapter D which I do think you need to tab, but we'll get to that a little bit later. So, what we're going to focus on, so if you look at Chapter D, the first thing that you will see is, let me actually pull this up in the manual, let me actually pull this up on the web. So, I have the manual pulled up right here, and so here's Chapter D, and this is where everybody should be at. So, when you open up Chapter D, the very first thing that you're going to see is it says, okay, here's like a brief organization of the chapter, and it'll say, okay, D1's on slenderness limits. We'll talk about that a little later. We're going to focus on strength, so we're going to go to D2, okay? And so D2 says, all right, there are several limit states, and here's what it says. It says the design tensile strength and the allowable tensile strength, so it sort of puts LRFD and ASD together. Remember, are we going to focus on this number? We're not going to ignore it. We're doing LRFD, okay? So the design tensile strength shall be computed as follows. So what it says is, all right, so we have tensile yielding, so this is the yielding limit state, and it says Fy times Ag. What do we think Ag stands for? Maybe the gross area, right? And so we have the yield stress times the gross area, and so if we wanted to calculate the design resistance, we would say Fy times Ag times 0.9, right? Because 0.9 is our resistance factor for LRFD. And don't worry, we'll put all this together here in about a week. We're going to take each piece of this and dissect it, and then we'll put it all together in one big old problem a little bit later. Okay? So this is gross section yielding. Okay? What about net section fracture or net section rupture? And by the way, I'll use the term net section fracture and net section rupture probably interchangeably. But what this is saying is that we are going to take the ultimate tensile stress and multiply it times this term AE. What is AE? AE is the effective net area. How do we calculate the effective net area? Well, we take the net area and we multiply it times U. Okay? And I will admit, I know that this seems a little convoluted. I will just go ahead and tell you that structural specifications do tend to do that. Like you tend to have to hop around a little bit to do a particular problem because of the way they're organized. And so I'm giving you a slight crash course into that, but don't worry, we're going to digest it a little bit later. So this would be how we would compute our gross section yielding limit state. For our net section fracture limit state, we would say 0.75 times FU. And then what I tend to do is say, well, instead of an effective net area, just the net area times this term U. Okay? So today what I'm doing is I'm throwing a lot at you. And what we're going to do over the next few days is digest each one of these terms one by one. And so for the next 2 days, the only thing I want to focus on are these two right here, the gross area and the net area. It's the only thing I want to focus on. And don't worry, we'll take our time with this as we go. Sound good? Okay. So my goal for today is, if I go back to this slide, my goal today is to try and figure out how to compute this area and how to compute this area. That's all I want to focus on today. Okay? All right. So let's go back here. So here's my section of the manual that I had just pulled up. This is what I'm looking at. We're going to look at gross area and net area. Okay? So can somebody just, which is bigger, gross area or net area? Gross area, right? Because the gross area is the main body of the member, and the net area is the gross area, but there's been stuff removed from the area. There's been stuff removed. So if we want a big picture idea for net area, like this is in general, that if we have a bolted connection, we can say the net area equals the gross area minus whatever area that we have removed from the connection due to the presence of bolt holes. Right? Does that make sense? So don't worry, we're gonna develop a specific formula for net area later. But for now, we're gonna need to understand three quantities about a connection. So the idea, our goal now, let's say our goal is to compute net area. Well, if we want to compute net area, let's just sort of put this in our head a little bit. We're going to need the gross area. Like, you can't calculate the net area without the gross area. And the gross area is either going to be something we compute or something that we look up from the manual. We're going to need the thickness of the medium through which the bolts are going through, which again, that's something we might need to look up. But we're also going to need the diameter of the bolt, right? Or the diameter. But I say the diameter of the bolt, but I didn't actually say this right here. Let's talk about the diameter. What diameter am I talking about? Okay? So when we're doing net area computations, okay, what we need is a hole diameter, not a bolt diameter. We need the hole diameter. We need, specifically, an effective hole diameter. So I have right here a bolt, and I'm going to say that the bolt diameter is D sub B, okay? The first point I want to make to you is that when we drill the hole, we do not drill the hole to the exact diameter of the bolt. It doesn't work that way. Specifically, what we do is we drill the hole a tad larger, okay? For standard size bolts that are up to an inch in diameter, we drill the hole a 1/16 of an inch larger, okay? And we'll get more into bolt details a little bit later, but for now, we'll just use this. So the idea is, if I have a 3/4 inch bolt, I do not drill a 3/4 inch hole. I drill a hole that is 13/16 in diameter, okay? Because the hole has to be just a little bit bigger than the bolt in order to be able to put it together. Anybody who's ever done any sort of work on a car or work in a garage knows that the bolt hole has to be just a little bit bigger than the bolt, right? And standard size bolts in structural steel connections are 1/16 of an inch larger, okay? But the other thing that we do, so whenever we're looking at the hole net area, we use an effective hole diameter. So the actual hole diameter is a 1/16 of an inch bigger, but we add another 1/16 of an inch to account for what I'm calling damaged material. So the idea is that when we look at the plate of steel, okay, we're assuming that this little lip of material around the bolt hole really isn't effective in transferring stress to the main body of the member. It's just kind of a rough surface condition, so we sort of remove that from the area. And the idea is that whenever we're calculating net area, what we do is we take the bolt diameter and we add an 1/8 of an inch to it to account for the hole diameter. And where do we get an 1/8 of an inch? Well, it's not really an 1/8 of an inch. We're adding a 1/16 twice. We're adding 1/16 for the actual physical dimensions of the hole. We're adding another 1/16 for that lip of damaged material around the edge of the connection. Does that make sense? Now, I'll say this is for standard size holes. If you ever had like an oversized hole or a slotted hole, this 1/16 might be a little bit different, but that's also a section where you can look things up in the manual. And don't get me wrong, or let me just say this, we are going to have a specific section of the course devoted just to bolted connections. So we're going to talk about this stuff in a little bit more detail later. Okay? Everybody okay with this? Okay. So now what I want to do are some examples. Okay? So I've got two examples, and I want to go through these together. Okay? So let me pull up my handy-dandy notebook here. Okay? And I have here a plate, and I want to determine the net area of this plate. Okay? So the plate is 8 by 3/8. And so what I mean by the 8 by 3/8 is this is 8 inches wide, and it's 3/8 of an inch thick. Okay? That's what I mean by the 8 by 3/8. And we're going to use 3/4 inch diameter bolts. 3/4 inch diameter bolts are among the most common that are used in structural engineering applications, period. 5/8 are kind of common. 7/8 are pretty common. 1 inch is pretty common. Those are the most common bolt diameters that you'll use. most of the example problems that we will do in this class and the calculations, like, unless I otherwise note, 3/4 inches is a pretty good assumption, okay? The only other thing I wanted to point out is this break line right here. So this doesn't really matter a whole lot for this problem, but it will on Friday. So what I'm saying is that the main body of the member is like out here. So this is where the gross section is. So it sort of means that this is the lead line, okay? It's not really going to matter today. It will matter a lot on Friday, okay? Is everybody with me so far? Okay, so let's use our noggins a little bit, okay? So how do we compute the net area? Well, conceptually, what do we think the first thing that we need to do is when we compute the net area? Tell me, if we were going to compute the net area, what's the first thing we need to do?
Find the gross area.
Find the gross area. It's 100% right. So let's talk about the gross area. All right, so okay, can everybody read that? Okay, so what is the gross area for this plate? Somebody take a stab at it. What do you think it is? I promise I'm not trying to trick you.
8 times 3/8.
8 times 3/8. There you go. 100% right. Okay. So we'll say that the gross area and I think I can do that one in my head because 8 times 3/8, the 8's cancel, and that's going to leave me with a 3. Okay. All right. So far, so good? Okay, now the next thing I'm going to do, and I'll walk you through this one a little bit, is let's just really quickly look at the effective hole diameter. Now, in this problem, I told you that the bolt diameter is 3/4 of an inch. If the bolt diameter is 3/4 of an inch, what can you tell me about the hole diameter, or the effective hole diameter, I should say? An 1/8 of an inch bigger. So the way that we compute that is we say that the effective hole diameter is the bolt diameter plus an 1/8 of an inch. And what is 3/4 plus an 1/8? 7/8. Okay. With me so far? Okay. All right. So now let's see if we can come up with an expression for net area. Okay, let's see if we can figure this out. Okay. So what do we generally know about the net area? We know that the net area equals the gross area minus the area lost due to the presence of bolts, right? Okay? So if I wanted to write a formula, I could say that the net area equals the gross area minus something, right? Okay. Samurai sword or lightsaber. I'm cutting like this, right? So how many bolts did I cut through? 2. And my art is really bad. It should be through the center of the bolts. So I'm cutting through 2 bolts. So maybe I should say it's minus 2 times something. Okay? So I seem to remember from basic dimensional analysis that if I'm adding and subtracting quantities, that they have to have the same unit structure. So what I can't do is I can't say the area minus diameter. That doesn't make sense. What I have to have is I have to have an area minus another area. So I have to have basically, I don't know, 2 times the area of a hole So what is the area of a hole?
ID squared over 4.
Pi d squared over 4. That is a very understandable answer. It's wrong.
Diameter times thickness.
That is the right answer. And to explain that, let me explain what's going on here. We samurai sorted or lightsabered through this, right? Let's look at this in 3D. Okay? So there's that. Move that over here. Okay, so I'm yanking on the plate like that, and I've got these holes going through the top. And then where I cut, essentially, was this. I had hole, 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 hole. And I sort of cut like that and like that, right? Okay, so I've got this whole thing going on. Okay? And so really the net area equals the gross area minus these. That's what I'm subtracting, right? I'm not subtracting a circle because I'm not looking in plan view. I'm looking at the section view. In the section view, I'm subtracting these. And what is the area of this? As you said, it's the diameter times the thickness of whatever I'm going through. Does that make sense? So I take the effective diameter times the thickness. So now let's calculate this out. And what was the thickness again?
3.
And can somebody give me an answer on that? We'll say 2 decimal places. I don't think you need to go any further than that. What's that? 3.66?
0.66.
Check that again. That seems a little high.
I was just looking at that right
It's Tim's fault. What's that? What's that? I didn't hear the. Somebody got a number?
2.344.
Okay, so we'll call it 2.34. Do I have a second on that?
Yes.
Okay. All right, so the net area and so that's going to be our answer. All right? Does that make sense? Any questions on that? Does it make sense why we're doing diameter times the thickness and not pi d squared over 4? Okay. Ready to move on? Okay. Let's look at our next problem. Okay. Now let's take a look at this problem. Okay, you can go away. All right. So now what we've got is we're going to compute the net area for a W10 by 49. Okay. So does everybody kind of see where the bolts are going through? See how the bolts are going through? What are these? The flanges or the webs? The flanges. Okay. So we got a bolt, bolt, bolt through the flanges. Okay. This is a W10 by 49, okay? So we're going to need to compute the net area. What is the first step in computing the net area of anything? What is the gross area of a W10 by 49? It's almost like you got to look it up in your handy-dandy AISC 16th edition steel construction manual. See, I told you we'd be using these. So this is where everybody that brought their AISC 16th edition steel construction manual gets to open it up and see where everything is. I know that some of you are probably still waiting on it to be shipped, so that's okay. It's all right. But 4 weeks from now, when you don't have it with you, what I'm going to do is I'm going to point at you, and I'm going to do this. But I know some of you are still waiting on it to be shipped, so that's okay. For those of you that have it with you, does anybody have a value for the gross area?
14.4.
Okay, so we'll say, so here's what I'm going to do. Okay, it's 14.4 square inches. And just tell me right off the bat, what table did you get that out of? Okay. And for those of you that do not have your manual, that's okay. So here's the manual. Probably going to be, let's see. Okay, so we're in table 1.1. A little further ahead. Probably right here. Okay, here we go. So we're on table 1.1. We're looking at the W10 by 49. So we're looking at that table right there, and we're looking at the area. So you can see the area in square inches for a W10 by 49 is 14.4. Everybody see that? So I do kind of like this new interface for the manual because I can do stuff like that and everybody can kind of see what I'm looking at. Okay. So let's go back here. Okay. So the gross area is 14.4 square inches. Okay. All right. So the next thing we're going to need, that keyboard keeps popping up. I don't like that. Okay. So the next thing that we're going to need is the effective hole diameter. And just like before, we're going to need that. Or we're going to do that, I should say. Because it was 3/4 of an inch, so we add an eighth and get 7/8. Okay? Sound good? Now, let's talk about the net area. So the net area is going to be the gross area minus the area lost due to the presence of bolts. So how many bolts are we going to subtract? 4. Because, so here, let me do this. So if we cut a section, you know, like through right here, you know, so we're samurai sorting, we're going to cut through that hole, that hole, that hole, and then there's going to be a hole back there that we're going to cut through, right? So those are the holes that we're going to eliminate, okay? So the net area is going to be the gross area minus 4 DE, but times what? The diameter times what? The thickness of the flange, right? What is the thickness of the flange?
0.56.
No fractions. We don't use the fraction terms, okay?
5.6.
0.56. Okay, so yeah, this is a very easy thing to do, okay? So remember, for the flange thickness, so we have that, and we have that. We do not use the detailing dimensions, we use the design dimensions. So we use 0.56, okay? Everybody okay with that? Always use the decimal dimensions. So I'll put note. And I'm going to put the T sub f does not equal 9/16 for the purposes of design. Sound good? So now what we'll do is we will say, all right, let's compute this out. Then 7/8. Okay, and so what do we get for this? 12.44. Do I have a second on that?
Second.
So 12.44. Boom. Okay. Any questions? This isn't so bad, right? Okay. So let me give you a couple of housekeeping items. So let me show you the next homework assignment. I don't know why these are highlighted like that. I'm not sure. But anyways, so here are the two problems I'm giving you on this homework. So I'm giving you, so we're going to compute the net area of this shape. So it's an MC 13 by 40. Because I know a few of you are still waiting on your manual, I decided to go ahead and report some of the relevant details and dimensions here. And I'll probably do that for this assignment and the next one. After that, you'll need to start looking them up. So I'm giving you all another week on that. I'm sure the weather isn't making shipping all that much easier. Okay? So here's this one, 5/8 inch diameter bolts. And then on this one, so this one's a WT 12 by 38. The thing about this one to keep in mind is that the bolts are going through different parts. Okay? So we've got bolts going through the flange and the stem. So you just need to be aware of that when you do your calculations. Make sense? All right. Any questions? Okay. All right. I do want to give you a slight peek into what we're going to talk about on Friday. Just to sort of make the point, and then we'll call it. So, first off, would it be fair to say that right now, this is sort of our formula for net area? That the net area equals the gross area minus the area lost due to the presence of bolts. I am saying that this is the formula for net area so far. This is not our complete expression for net area, because what we're going to do on Friday is add this, okay? And these are what are called stagger factors, okay? What are stagger factors? Stagger factors are intended to deal with bolted arrangements like this, okay? Where instead of the failure path doing this, the failure path might do that, okay? And so there are these diagonal failure paths that change the net area, okay? Now, I'll tell you, and I just want to sort of make a very strong point in this class, that I don't do anything in here that doesn't have a real-world application, okay? So, let me sort of make this point. So I've drawn the net area failure path for what I'll call a parallel bolt arrangement, which is what we did today, and this is a staggered bolt arrangement. Some of you are probably thinking, why in the heck would you do this in the real world? Why? There's a very simple answer to that. Which path do you think has a bigger net area? Parallel or staggered? Staggered, okay? It's a bigger area. Why would increasing the net area matter? How are we going to compute the strength of a member? We're going to take the area and multiply it by some limiting stress. So let's assume these are both made out of the same steel. If these are both made out of the same steel, which member do you think has the potential to be stronger, parallel or staggered? So staggering the bolt arrangement can increase the net area. Increasing the net area can increase the capacity. Increasing the capacity means maybe we don't need to use as large of a member to withstand the same amount of load. And why does that matter? Money. Saves money. So there is a real reason why you would do that. It's not just what have you. I mean, think, all you have to do is change the bolt pattern and you can make the member lighter. Wouldn't you do it? Yeah, you probably would. You know, it's not going to make it any more difficult to put together, you know. Because, I mean, what are they going to do? They're going to take it to the side, stick a bolt through it and tighten it. Stick a bolt through it and tighten it. That's not going to change labor at all. But it can definitely change on cost. It can change lower your cost. So, again, I'm not showing you something in here that you're not going to see a real-world example of. Okay? So I want to make that crystal clear. Okay? Excuse me. Sound good? All right, any questions just about the idea? We're going to talk specifically about how to handle this and what stagger factors are on Friday. You aren't going to have to worry about that for today or for your homework assignment. Sound good? I'm going to pull the code up one more time. I will see you all on Friday. I'm giving you 9 minutes of your life back. Try and stay warm.